Hello, and welcome back to Prolumnus. Let's look at derivatives today. Now, a derivative is an idea of a generalized slope. You've probably heard of slope discussed in terms of rise over run, where you would look at how sharply a function increases based on the difference in the function's input. Now, a derivative can do this for any kind of function that is continuous along the derivative. Now, that includes functions that have weird curves in them. Usually rise over run would be used for linear systems, but here you could take the slope of parabolas, of trigonometric functions, and anything as long as it obeys the laws of being continuous. The reason this works is because if you look at a curve closely enough, if you zoom in more and more, it starts to look like it were a straight line, which means you can use the sort of rise over run technique on very, very small scales, and that will give you an approximation of that slope. And you can actually use limits with rise over run to give you an exact answer for the derivative. So let's look into that. So in order to display this rise over run concept, here we have a parabola. Now let's say you wanted to take the derivative at this point here. One way you could do that is to take some approximations. Now the exact answer would just be a flat line that only touched this point. So it would look something like this. So this is sort of the goal of what you're looking for, is this exact slope. So one of the ways that you can go about this is that you can basically just take a guess. So if you have a point right here, you just take a guess of where we could have these 2 points connected, and basically if you have those 2 points, you can make a line with them. And we can sort of have that be our guess for what the slope is. It's not a good guess, and it's been exaggerated so that you can see the difference. But we can always do better than this. So you could take rise over run of this and get something sort of close, but what you could do is you can take this point and bring it a little bit closer. So you can actually move this point closer to this point. And you get a guess that would be still a little bit off, but slightly better. And you can keep bringing this point closer and closer. Again, not exactly rise over run. You can keep getting closer and closer. And finally, you would get to a point where you would have your guess would be exactly this point. And if that were the case, then you would have this line would become this line. So let's go ahead and label these points. So this would be, we're going to call X. And we're going to call this point that we're moving, we're going to call it, it's going to be at a point X plus some extra little bit that we can change. So this will be a variable that we'll call delta X, which means that the distance between these 2 points is that variable, that delta X. So we have control over this distance here. So if you were to write that as delta Y over delta X, well then you have to use this rise over run formula. So you would take the function evaluated at this point and subtract the function evaluated at this point to get this rise, because you would have the function evaluated up here and the function evaluated down here. So you would start out with f evaluated at x plus delta x, this point here, minus f at just x, the point that we're looking for the derivative, divided by our run. Now the run is just our displacement here, this delta x. So for any finite value of delta x that's non-zero, this is very, very difficult to figure out if you're just looking for an arbitrary point, because it's not exactly what your line is. You can get infinitely close, but you're never actually going to make this line exact until your guess becomes this point, meaning that this delta x becomes 0. But that means that you're dividing by 0 here. And that's a problem because this would mean that you would have 0 divided by 0, and that can't happen. You can't divide by 0 like that, so you know that this approach is not going to work, at least not the way that we're doing it here, not with this sort of guesswork. What we need is a limit. So you can actually take the limit as this approaches 0 and understand that behavior. So take limit of your function, so of delta y over delta x, which is this function here, and take it as delta x goes to 0. Now, technically, this doesn't work at 0, as we have already showed, but you can actually see that this would be the derivative of your function. And this is how you would write derivative. It would be d over dx. D just being a way to write a very small delta, or a very small change. So even though using algebraic methods, we cannot definitively say what the slope of this line is, using the limit, we can actually evaluate this exactly for any value of x, because as shown in the video on limits and the practice video, when your delta x goes to 0, you can actually still understand what is happening when the distance here shrinks and they become one and the same. That you can still understand what's happening at that point in the function. Now in the next videos, we'll go over some more practical uses for this, and we'll show this more explicitly with some example problems, and it'll make more sense seeing what happens if you put actual numbers in here. But for now, try and see how this is working, and you can even try this yourself, that this sort of guess and check work, that you can start to imagine that these lines would become the same. And you can try for your own problems to see if you can figure out how this would work using the concepts that we have derived in our limit videos. So just to show the whole thing, this is the full written expression for the definition of a derivative. Now these you can see that we have derived from up here, so hopefully it looks a little bit less intimidating. But this is really only a mathematical tool. You could calculate derivatives this way, but the great thing about a derivative is that once you've done this a single time, you can derive some rules for how you can use this relationship in order to be able to do this side much more efficiently without having to do all of this. And we'll also have a video covering those rules in order to speed up your derivative calculations. So that'll be it for the concepts of the derivative. Look out for the future videos in the calculus series. If there's anything you'd like for us to cover, please feel free to let us know in the comments down below. Thanks for watching, and see you in the next one.